So now we've established our kinematic equations for angular motion. We're going to tie these together. So just to remember that for constant acceleration, we have our linear kinematic equations, so stuff moving in a line, and then we have our angular. And these things are analogous, we just change the variables. So position linear is x, and then it becomes theta over here. And so on. I'm not going to go through it all. So we're going to tie these together because we can talk about linear motion even though it's not really in a line, it's in a circle, but same thing. We have this bar that's rotated through some angle theta. And so for rotation, we could talk about theta, but we could also talk about maybe like a little segment on this, the very end of it maybe. So this section right here. Well, this section here has rotated through that angle, but it's also covered some distance here. This should be familiar from circular motion, but it's covered some distance here, which is the arc length of the circle. And then the length of it, wherever it is, would be r. And that doesn't matter. It doesn't have to be the radius. We could also do it, we could say this point right here. This point right here, then we would have a new r. So this would be like r prime or something, r2, whatever. It's just how far away from the axis of rotation you are. Okay, so let's get some relationships here. Well, we know that theta in radians is just the ratio of the arc length to the radius. And then if we rearrange that, we get that the arc length, the linear distance, is equal to the angular distance times r. So we have the linear component. This is linear. And don't get confused because yes, it's arcing, it's a circle, and angular. Okay, then what we could do is let's take the time derivative of the linear position. So the derivative of the linear position with respect to time would be, we have to derive on the other side with respect to time. And r is constant, so we can just leave that alone. And you can see where this is going because the change in position with respect to time, that is velocity. And the change of angular position with respect to time is angular velocity times the radius. And this speed here is the tangential velocity. So it's how fast it's moving along here. So we have the velocity. So we take for the linear velocity, it's the angular velocity times r, just as the linear position is the angular position times r. Now, if we take the derivative of velocity with respect to time, and again, r is constant, so we get the change in velocity with respect to time is the acceleration, and the angular acceleration times r. And this acceleration is the tangential acceleration. So it's how fast is it accelerating this way. We could use the same relationship for non-uniform circular motion. But so for linear acceleration, it's the angular times r. I guess the last thing we could do is use centripetal acceleration. Centripetal acceleration is v squared over r. And the velocity is the omega. So we get centripetal acceleration in this case is going to be omega r squared divided by r. So we get centripetal acceleration would be omega squared times r. And I think we've already derived this, but there you go. So this is the relationship between them. Basically, for your linear whatever is going to be your angular times r, where it is. So that's in general. I guess I'll do one example and then give you some problems. You know what? Instead of doing an example, I'm just going to give you the problems. So it's nothing. It's not that. There's really nothing new that we're introducing except going from angular into linear. And I could do one example, but the problems that you'll get will be different. So I don't know if you could really rely on it. But we'll do these and we'll work through them in class though.